anthraquinone. And these oxidations are quite easy. One thing I didn't mention last time was that the oxidation of this compound and this one usually takes place under much milder conditions than the one that has no hydroxy. But you end up oxidizing that central ring to what's known as a 9-10 using the numbering system, 9-10 anthraquinone. Then I mentioned that this compound, adriamycin, was an anti-cancer antibiotic. I can't remember when it was discovered, so I went and looked it up. Actually, it was discovered before 1968. This is covered in a 1968 patent. So it's been around for a long time. Now, one thing I wanted to point out was that this molecule is composed of really two parts, right? You have this anthraquinone, which is fused to a cyclohexane ring, and then there's this piece hanging off it, which is a rare sugar called inosamine. Now, we've talked about solubility properties way back when. And one thing you need to know is that anthraquinones, compounds like this, are really insoluble in just about everything. Okay, so yeah, they will go into some organic solvents, but not easily. And certainly, the solubility in water is miserable. And so one of the functions of these sugars, which have an amino, a hydroxy, and in this case an ether, is to confer water solubility on these compounds. The last thing I mentioned was cochineal, and I said that was another anthraquinone that you have probably encountered. This is the structure, and a little bit complicated. You'll notice here's the anthraquinone nucleus. Of course, you have substituents all the way around, and interestingly enough, you have another sugar. Okay, so in this case, this is a very common sugar. This is D-glucose, and this compound, as you can imagine, carmine, it's bright red. It's FDA approved for use in foods and drugs. And it comes from an insect, okay? So it's a little scale insect that lives off of, I think, prickly pear cactus. And this is, which is how they get it. They collect the insect pest in Mexico and Guatemala and places south of the border, and then they extract this stuff out. So it's likely that the scale insect doesn't have the biosynthetic machinery to make this, that this comes probably from Streptomyces, one would imagine. Now, I want to draw your attention to the sugar here. And notice that here you have a carbon-carbon bond that joins the anthraquinone to the sugar, whereas in adriamycin, you have a carbon-oxygen bond that joined this piece to the sugar. This is known as an old glycoside, and this is going to be known as a C-glycoside, okay? Now, let's see if you learned anything. Okay, so let's draw D-glucose here again, okay? So this is D-glucose, and both isomers at this position are D-glucose. We're going to see that this is a carbon atom that's the equivalent of an aldehyde. So that comes in a chapter or two. But for now, let's just look at what's known as the alpha isomer, which is the oxygen here and the hydrogen there. Beta has these two switched. Now, if you wanted to form, so imagine breaking this bond in your mind, and I want to make this bond because this piece is prepared biosynthetically separate from that. And at some point, this carbon-carbon bond is formed. Okay? So imagine that I have D-glucose on the one hand, and I have this anthraquinone on the other hand. So the microorganism that probably biosynthesizes this has these two building blocks that come together somehow, and you're going to tell me how, to form carminic acid. And so we're going to take a look at this. aromatic ring? It's got two ketone substituents, right? And it's got hydroxy, hydroxy, hydroxy. Would you expect that to be activated towards electrophilic aromatic substitution or deactivated towards electrophilic aromatic substitution? Well, what kinds of substituents activate? The ones that activate are the electron donating ones, right? What kinds deactivate? Nitro, sulfone, ketone, and whatnot. So it's got two deactivating substituents and three very strongly activating ones. And so this is actually a very activated ring towards electrophilic aromatic substitution. So there's only one position right there that's open. All the others are substituted, right? So if anything happens, it happens right here. Notice that this ring has carboxylic acid deactivating, deactivating, one activating, and one slightly activating. So the two rings, this is the one where the action is going to take place, right there. So what did you have to do to join this carbon, make this carbon hold hands with that one, form that bond? This carbon has to bond to that one. Well, if it's done by electrophilic aromatic substitution, you needed an electrophile that was derived from what? From D-glucose, right? You needed an electrophile that's derived from this piece. So let's forget about all the hydroxys. Let's just, let's just look at the important part, that. Okay, so that's that carbon atom right there. You wanted to form a bond from this carbon to that one. And you wanted to turn this into an electrophile. How would you do that? Just think. Well, what kind of reaction would that be? That would be a Friedel-Crafts alkylation, wouldn't it? Huh? So we've seen Friedel-Crafts alkylations in the past. How did we do those? We started with alkyl halides, didn't we? And aluminum chloride. Well, guess what? In nature, you can't use aluminum chloride. That's not a reagent that we can use. But we did see, recall that we did see another kind of a Friedel-Crafts reaction, and we saw that Friedel-Crafts being used with cyclohexene. And I said that any reaction that gives you a carbocation can be used for a Friedel-Crafts. So now the question is, how do you form a carbocation right there? Well, it's very easy. You just treat this with acid, any kind of acid, let's just say proton. Okay, so this is going to be a reversible protonation of this alcohol. And now, just imagine what can happen. You have lone pairs here, and that can, and this is reversible, and that can give you a very nice, stable, because this is resonance stabilized now, cation, like so, and water, of course. Okay? That cation is what does the Friedel-Crafts reaction at that carbon atom, and that's what gives the carbonic acid. Okay? So I mention this because I think very often when you hear Friedel-Crafts and this thing, what's the relevance to anything that you know about? Well, actually, there is relevance. The relevance has to do with stuff like this. I mean, the biosynthesis of adiamycin also involves chemical steps that we've seen. So anyway, so let's now talk about the next little thing, which is practical applications of phenol oxidation. So phenols undergo oxidation even though there's no alpha hydrogen, right? So when we talk about alcohol to ketone, alcohol to aldehyde, aldehyde to carboxylic acid, when we had that discussion, remember we said that you need to have, for the oxidation of an alcohol, you need to have that alpha hydrogen. So in other words, if I have carbons like that, and here's the alcohol, this hydrogen atom right there is critical to getting the oxidation to work. And yet, if I look at phenol, this carbon atom is not substituted, and yet they still undergo oxidation. And the reason they do is because what? Because the mechanism is not the same. So aromatic alcohols, phenols that is, undergo oxidation, but through a different mechanism than aliphatic alcohols. And so the mechanism here involves hydrogen atom extraction from the hydroxy to give you this resonance stabilized oxygen-centered radical. Now this is known, when you have a hydroxy group here, this is known as a semiquinone. You don't have to remember that, but this radical is stable. Okay, so semiquinone radicals are quite stable. And so they have enough of a lifetime that you can then extract another hydrogen atom from the other end. And if you just draw the resonance structures for this diradical, it turns out it's nothing other than the quinone itself. So to go from the hydroquinone, from the dihydroxybenzene, the para-dihydroxybenzene, to quinone, this takes place in 2 steps: hydrogen atom extraction, hydrogen atom extraction. Now, it turns out that this is an important process in your bodies and mine, because oxidative damage to our cells is something that we need to control. Okay, so we live in air, we use oxygen, but oxygen is very often deleterious to our cells, and particularly if you get uncontrolled radical reactions taking place, a lot of damage is done. And so our bodies have vitamin E, or alpha tocopherol, and this is it's a big molecule, but the business end, as far as we're concerned, is all the way at the left. So you'll notice that we have a parahydroxyphenol. So this hydrogen atom can be lost to a radical rather easily to give you the semiquinone kind of structure. And what this does is it acts as a natural antioxidant. Okay, so it stops the oxidation process from going on and giving you radical chain mechanisms that in your cells that cause damage. Now, this is natural vitamin E. Let me ask a question. How many asymmetric centers are there? How many asymmetric carbon atoms? I asked you that question with respect to Adriamycin on Monday. 3. Yeah, you're right. 3. This one, and this one. Okay, now, it turns out that if you want to make synthetic alpha tocopherol, controlling the stereochemistry here, the absolute stereochemistry, ain't easy. And as a result, synthetic vitamin E is not one isomer, it's a mixture of isomers. And so the isomers here don't really matter very much. This is the business end, as I said. So you have this lipophilic piece, and then you have this hydroxy. And here's where the action takes place. Now, this business of inhibiting oxidation is something that you also encounter with your food, because it turns out, if you look at the labels on various manufactured foods, you'll find that they say very often BHT and or BHA added as a preservative. And so if you're like me, you kind of wonder, gee, what is this BHT stuff? And BHT is a really screwed up name, butylated hydroxytoluene, which is not systematic at all. But here are the butyls. Here, toluene, remember, is methylbenzene, so there's methylbenzene, and hydroxytoluene as well, there's no hydroxy. So that's BHT. BHA is butylated hydroxyanisole. This is usually a mixture of positional isomers. Now, how do these things work? Well, they work as follows. If your food sits around in air, of course, things get oxidized. And that generates radicals. Those radicals can go on and do radical chain reactions that typically degrade the quality of your food by making it rancid. And so what this will do is this hydrogen atom will get abstracted with a low activation barrier by that intermediate radical from your food. It will stop the chain mechanism, and it will form a stable oxygen radical. Now, this oxygen radical is not going to do much because A, it's resonance stabilized, B, those 2 T-butyl groups prevent it from approaching anything. And so what you end up being able to do is shut down radical chain mechanisms that will degrade the quality of your food. So these are common food additives, and they prevent our food from becoming rancid through air oxidation. Exactly what they do to us, I'm not sure, but they seem to have low toxicity, or we'd all have problems because they're everywhere. So, okay. So now let's talk about other kinds of chemistry of phenols. I just told you about in the context of the carbonic acid biosynthesis, I talked to you about what? About electrophilic aromatic substitution of phenols. And phenols are strongly activating towards electrophilic aromatic substitution. And so alkylation is not the only process. Bromination, as you would predict, takes place very readily. Now, when we try to do the bromination of benzene, remember we said something. We said that you take benzene, you throw bromine in it, and nothing happens. And that was how we got the discussion started. You have to activate the bromine by adding a strong Lewis acid that gives you a more reactive bromonium ion, and so on and so forth. Well, for phenol, you don't have to do that. You throw phenol into bromine, bromine into phenol, and because this is so strongly activated, you get a product. And no ferric bromide needed. And so this reaction is easy to do. It's much faster than the reaction with benzene because these electron pairs are donating into the ring. And so this ring is much more electron rich than the ring where you don't have the hydroxy group. And so that's manifested in this reaction, that the reaction takes place in the absence of a catalyst. So in other words, you don't need a catalyst to lower the activation barrier because the activation barrier is already low. Okay, now, if you do the reaction in carbon tet or in a similar nonpolar solvent, the reaction stops after a single bromination takes place. However, this compound is still strongly activated because of the hydroxy, so this is still going to want to undergo reactions with good electrophiles. And so, interestingly enough, if you do the reaction not in carbon tet, but in water, then you get essentially an instantaneous precipitation of tribromophenol. And so this is used actually as a diagnostic tool. If you don't have access to spectroscopy, you think you have a phenol, you just take a little bit of bromine water, and it decolorizes the bromine water, and you see a thick precipitate. Bingo, you've got a phenol in there. But notice that here, this has undergone exhaustive bromination. All three activated positions are brominated, and you get essentially quantitative yield. So now the question is, well, how come? Do the reaction in carbon tet, goes part way. You do the reaction in water, my goodness, you get a fast, complete reaction. Why? And there are actually a couple of reasons. First of all, in water, so bromine water is kind of an interesting reagent because the water actually reacts with the bromine. And what it gives you this hypobromite. This is known as, anytime you have a whole halogen, that's called a hypobromite. But this is a very reactive form of hypobromous acid. It's protein, so HOBR, H-O-B-R, is hypobromous acid. This is the conjugate acid of hypobromous acid. So that means that this is going to be a good source of Br+. Think of this as being the same kind of Br+ that you get when you add not water, but ferric chloride to or ferric bromide to bromine. Same idea. And so this is a reactive source, more reactive source of Br+ than this one. And so hypobromous acid is the stuff here, but this is the active brominating agent. So that's why it brominates better in water. That's one reason. The other reason is maybe a little bit harder to see. That in water, there's an equilibrium. There's not much of this. It's a minor component of the equilibrium, but there's a little bit of phenoxide. And so the phenoxide is even more reactive than the phenol as a nucleophile and reacting with electrophiles like Br+. And so this is the other reason why in water you get a very fast reaction. And you say that, well, if this is a minor component, how important can it be? Yeah, but this equilibrium is constantly being established. This is being taken out of circulation by bromination, so Le Chatelier's principle is pushing this equilibrium from left to right. And so you end up with a steady state concentration of the phenolate. The phenolate is probably what is getting brominated because it's so much faster than the phenol. And then there's another maybe minor point, but the second and third bromination in water are expected to be faster than the first. You can kind of expect it to be faster. Why is that? Well, because the phenolate is going to be more easily formed if you have an electron withdrawing bromine here. And so the equilibrium gets pushed further to the right with each successive bromination. Okay. So bottom line is, though, that you can you have nice control. If you do the reaction carbon debt, single bromination. If you do the reaction water, 3. So then the question is, well, okay, but I don't want single bromination. I don't want 3. I want 2. How do I do that? And actually you can do that too. You can stop the bromination after you introduce 2 bromines, look at that, 87%, by adding HBr. Okay, now why create that? And this is in water, okay? So tell me why it is that adding HBr will work. Well, because it suppresses the formation of phenoxide, right? You don't get phenoxide if there's acid around. No way. And so you end up being able to control the rates of the bromination very nicely that way. And so this is a nice example of why we study mechanism. Because if you don't understand mechanism, then none of this makes any sense at all. And if you do understand mechanism, then yeah, it does make sense, and it allows you to design experiments that will favor, say, the dibromo over the others. Okay, so that was what we needed to know about bromination of phenols. But of course, bromination was not the only electrophilic aromatic substitution reaction we talked about. We talked about a whole bunch of them, in addition to Friedel-Crafts. Talked about nitration, sulfonation, yada yada. And so the question is, how about the others? You know, can we nitrate phenols? And the answer is, yeah, sure, you can nitrate phenol, but there's a problem. The problem is this, that nitric acid is also an oxidant. And so remember that phenols are easily oxidized. And so if you try to do a direct nitration of phenol, you get a mixture of products. You get quinone and quinone-derived products, and you get some of the nitration. So it's not a good way to go. So now the question is, well, if I want to make a nitrated phenol, how do I do it? And the way you do it is come at it the other way. You take chlorobenzene, nitrate that, and then you do a nucleophilic aromatic substitution of hydroxide to displace the chloride. So you have control here too. In other words, try to do it directly, it's not going to work really well, because why? Well, because the nitric acid is going to oxidize your phenol and your yield's going to be crap. But if you do it this way, then you end up with good yields of product. So you nitrate this first. You can stop after the first or the second nitration, or the third. You can nitrate it selectively, because each successive nitration is slower than the first. So getting mononitro, dinitro, trinitro, not hard, right? Because each time you add a nitrogen, you slow it down. That gives you control. Now you can just do a nucleophilic aromatic substitution. Now, with 2 nitro groups, this should be a great reaction. Remember, for nucleophilic aromatic substitution, you need electron withdrawing groups, typically nitro, fluorine, or something strongly electron withdrawing. Chlorine is good. Fluorine is better. Iodine is worse, right? Because why? Well, because we're not breaking the carbon-chlorine bond in the rate-determining step. This reaction, remember, takes place in 2 steps: addition, elimination. It's the addition step that's slow. And so anything that is strongly electron withdrawing is going to accelerate that. Okay, so that's how you make nitrophenols. So does phenol work for Friedel-Crafts? Yeah, it does. But remember for the phenylcrafts, you have to use aluminum chloride to form that reactive, and I'm talking about the acylation right now, to form the acylium ion, which is the active electrophile. So you start with, remember how we did this, how we generate the acylium ion. You start with, let's just say acetyl chloride, and then you treat this with aluminum trichloride. This is a strong Lewis acid. You have electron pairs here, and so you end up with a Lewis acid, Lewis base product. And then this can just detach to give you tetrachloroaluminate minus, and in this case, this. And remember, this is the active electrophile, and that this is resonance stabilized. And that actually this is the more important resonance structure, because why? Because everything has a complete octet. Okay, but the point is that this is the electrophile that we're going to generate with the phenol, which means what? Well, it means that, guess what? You need to use aluminum chloride. However, the phenol reacts with the aluminum chloride. And so you say that, uh-oh, that means I got to add not one equivalent aluminum chloride, I got to add two. One to react here and one to react with that. And the problem here is that once it reacts, generates HCl, then this deactivates the ring. And so in the case of phenylcrafts, paradoxically, the phenol doesn't help, it actually hinders. Okay? Why? Well, because it reacts with the catalyst, and the ring that is now bonded to a positively charged oxygen atom is deactivated relative to phenol and relative to benzene too. So yes, you do get the product, but the reaction is slow. And you never ever get polyacylation. Stops after the first one, almost all. Not almost all, always. Okay, so we saw the reaction of phenols in the Williamson ether synthesis, right? We saw that phenol could be converted with sodium hydroxide to the phenoxide. This works really well because there's about a million-fold difference in acidity between phenol and water, right? You get water and sodium phenoxide here. And the difference in acidity is about 1 million, so this reaction goes to completion. This is a good nucleophile. And so now if I allow this to react with, say, iodomethane, methyl iodide, if you will, then I will get a SN2 reaction, a substitution, a nucleophilic substitution reaction that will give me from phenol, it will give me methoxyphenol, or remember this stuff goes by the trivial name of anisole. Okay, so that was the reaction that allows you to form that oxygen-carbon bond. Now it turns out that oxygen-carbon bond can be cleaved, and it's not hard to cleave it, but of course under different conditions. So phenolic CO bonds, not to the aromatic ring, the other one, are labile. And so if I take that methoxybenzene that I just formed and I treat it now with HBr, what's going to happen? Well, you know, it's pretty easy to see what's going to happen. You have electron pairs, non-bonding electron pairs on the oxygen atom of the methoxy. You have a proton, so of course you're going to get an acid-base reaction, reversibly. And once you have the acid-base reaction, look at what you've done. Now look at this methyl group. This methyl group is bonded to a pretty good leaving group here. And so now I can do an SN2 reaction of the bromide attacking the methyl to generate methyl bromide and phenol. So it looks like sort of the opposite of the Williamson ether synthesis I just showed you. And the reason it works is because by adding acid, I can convert the phenol or the phenoxide rather, into phenol, which is a good leaving group. Easy. Now, with the Williamson ether synthesis of aliphatic ethers, we have to worry about regiochemistry sometimes. We have to worry about that bromine, and we've seen this reaction in the aliphatic case, by the way. This is not new. So go back, when we talked about substitution reactions, we talked about this reaction. So, but in that case, we had an aliphatic group, sp3 carbon on both ends, and we have to worry about does it react at this end of the ether, does it react at the other end, does it react at both ends, and whatnot. Here, there's no issue, because there's absolutely no way you're going to get an SM2 and an sp2. If you did, the bromine would have to attack from inside the ring, a physical impossibility. It would have to attack on an sp2 hybridized carbon, and you would get inversion of configuration, which would be a trans double bond. And so, under no circumstances is this going to happen. The only way this is going to react is as I've shown up here. So this is a very common way of cleaving aryl ethers and getting to phenols. Now, you have to use conc HBr for this. No, you don't. A very good reagent for this is boron tribromide. Now, how does that work? Well, it works the same way. That's how it works. If I take this compound and I allow it to react with boron tribromide, there's boron tribromide. Boron tribromide has boron bonded to three things. Does boron have a complete octet? No. How many electrons does it have for octet rule purposes? 6. Right, which means it's 2 electrons short, which means it's a Lewis acid, which means this process will take place essentially in one direction. And it will give us that charged species. Okay. Now we're in the same place we were before. Instead of having a proton here, we've got boron here. So you still did an acid-base reaction with the electron pair of the methoxy group. You have a positively charged oxygen, so guess what? That methyl group is now activated towards nucleophilic attack, in this case, again, by bromine. So this species can lose Br minus. That Br minus can attack the methyl group, spit off methyl bromide, and give you a boron phenoxide. All 3 bromines are reactive. Okay? And then when you work up the reaction, work it up with acid, you get your phenol back and you get boric acid. So it works exactly the same way as we've seen all along. So this can give you the bromide, and the bromide attacks here like so. You get methyl bromide, and then you imagine phenyl OBBr2. These 2 bromines are still reactive, and so it keeps going until you either run out of bromines or you run out of that. Okay, so this is not, nothing we've talked about in this little discussion is particularly new. It makes use of SN2 chemistry. It makes use of a little trick that we learned way back when, that you can make ethers and alcohols into good leading groups by adding acid. And you saw this now with a Bronsted acid, HBr, and you saw it with a Lewis acid, which is BBr3. Now, I mentioned that there was another palladium catalyzed coupling reaction we were going to get to, and so now it's time to talk about that one, the Stille reaction, named after the late John Stille, a professor at Colorado State, who tragically died in an airplane crash. It was a passenger flight that went down some years ago. It was just bad luck. The pilot was just fantastic, but they had an accident, and a piece of metal severed the controls to the tail assembly. And somehow this pilot, who, I don't know how he did it, he managed to fly the plane just with the flaps, and actually was able to land it with the flaps. But he didn't have good control, so he landed it, but then one of the wingtips caught. Make a long story short, 2/3 of the people survived, 1/3 didn't. Pilot survived, but John Stille wasn't one of the lucky ones. So this reaction is named after him. He discovered it. And it worked. By the way, the Stille reaction works with aryl bromides, iodides, chlorides, but it also works with triflates. And triflates are kind of nice because you can convert a phenol to a triflate very, very easily. So this is trifluoromethane. There's a trifluoromethane, sulfonic anhydride. So an anhydride, if I add acid to this, I'm going to get two molecules of trifluoromethane sulfonic acid, triflic acid. And so we've seen triflic acid before. So you take pyridine, you take triflic anhydride, you convert the phenol in essentially 100% yield to the triflate. Now, the triflate, you can think of this carbon-oxygen bond as being polarized strongly in the direction of the oxygen, negative charge out here. So in that respect, that carbon triflate bond looks a heck of a lot like a carbon-halogen bond, where the carbon has the partial positive charge and the halogen has the partial negative charge. And so it shouldn't come as a complete surprise that aryl triflates react with these palladium, in these palladium catalyzed reactions very similarly to aryl halide. So if you have the triflate or the halide, pretty much the same. So just this palladium zero does an oxidative addition to the carbon-bromine bond, you do an oxidative addition to the carbon triflate bond. And so you can use these triflates, by the way, not just for the Stille, you can use them for the Heck, for the Suzuki, and for the Negishi that I guess we're not going to talk about. So these work. And so here's how it works. The reaction that this is closest to is the Suzuki that we talked about. The Suzuki used a aryl boronic acid and an aryl halide or triflate. This doesn't use an aryl boronic acid, it uses an aryl stannane, an aryl tin bond, an aryl tin compound. So where for the Suzuki we have boron hydroxy, here we have tin with usually methyls or butyls. And so this is an aryl stannane. These are very stable compounds. This one, you can buy this. It's this I think is a liquid actually. I don't think it's a solid. And so you can allow this to react with a triflate. Notice that you have an unprotected ketone, catalytic amount of palladium 0, and an excess here of lithium chloride. So you need to do this reaction in the presence of chloride, as it turns out. And if you do that, you end up with the new red bond. Same way we saw for the Suzuki reaction, really. Doesn't look much different. You get very good yield for it. The byproduct is trimethyl tin chloride, so the trimethyl tin and one of these chlorides gets together, and you end up with lithium triflate. So these are removed from the mixture during workup. So it looks again like the same mechanism that we saw for the Suzuki, and you're right, it is the same mechanism. And it's the same mechanism as essentially all of these cross couplings. And so how do they work? Well, the first thing that happens is that you get the oxidative addition of the palladium to the carbon triflate or carbon halogen bond. So palladium 0 inserts here. It's the first thing that happens. And then after that, you get some ligand exchanges. And then the last thing that happens is you get a reductive elimination that brings these two things together, bonded. And so let's take a look. Now, we started with tetraglycerolphosphine palladium again, which is palladium 0, but it's 18 electron. And so we need to do a couple, so 18 electron palladium. Now we need to, I've summarized 2 steps here. We need to detach 2 of the triphenylphosphine L-type ligands. And that gives us a 14 electron palladium species, which does the oxidative addition. And so this does the oxidative addition. There it is. I've inserted palladium into the aryl triflate bond. And now the triflate is displaced by chlorides. This is a ligand exchange. Remember ligand exchanges? They take place X for X or L for L usually. So this is an X ligand, triflate, being replaced by chloride, another X ligand. So X for X, L for L for ligand exchanges. So you then do another ligand exchange where you form, and this is the step where you form the tin chloride and you form the palladium bond to the other piece. Now this just does the reductive elimination, regenerating your catalyst and giving you the red bond. Now this is all very nice. This reaction works really well. And so there are cases where the Suzuki is, maybe a little bit dicey, and if you need to get to that product, the Stili is the go-to reaction. That's the good part. Bad part is it uses tin. Tin is toxic. Tin is toxic, and these alkyl pins are particularly nasty. So the tetraalkyl, low molecular weight alkyl pins are volatile. They're gases. I mean, they're solids, but they evaporate. And they are nerve toxins. And so if you breathe them by accident, or when I breathe them, people have different reactions. It's really weird. You get kind of a sensation in your mouth. Okay, I don't know how to describe it. You don't really taste it, but you feel something that you can't describe in your mouth. That's really bad. That tells you that it is doing something to your nervous system. And so these kinds of compounds are not going to be useful in pharmaceutical manufacturing. And so the pharmaceutical industry really can't use Stili reactions because they won't use tin on large scale. And so this is okay for the lab scale, but large scale, no good. They are useful, however, for a small scale. Now, how do you make these? Well, you make these, interesting enough, through Grignard. So you start with the bromide, make a Grignard, you know how to do that. And then this trimethyl tin chloride, which is volatile, neurotoxic, nasty, but you can use it. It just kind of alkylates it gets alkylated by the Grignard. So if I look at this looks like a very strange reaction to me. Because look at what I'm doing. I've got a carbon metal bond, carbon bromine, and I treat it with tin chloride and end up with another carbon metal bond. And so the question is, well, what drives this process from left to right? I mean, why didn't I start with this, treat it with dibrommagnesium or brommagnesium chloride, end up with tin chloride and the Grignard? Notice why does it go from left to right and doesn't go from right to left? The answer to that is because of the difference in electropositivity, if you will, of the two metals. And so magnesium is further to the left on the periodic table than tin. And so magnesium is more electropositive than tin. And so you can always go from the more electropositive to the less electropositive metal this way. So you can make these from the tin. Now, what does that really mean? Well, it means, interestingly, that so this comes from the bromide. You could have used the bromide there. And so what the Stili reaction allows you to do, in fact, you can do this with the Suzuki too, is it allows you to couple two carbon atoms that have the same polarity, right? Because carbon bromine is carbon bromine on the left or on the right. And so, yeah, you can see why that might be an interesting or a useful thing to be able to do. You need to think about what I just said about the polarities being mismatched. Typically, when we form a carbon-carbon bond, what do? We have a delta plus and a delta minus. They come together. But here, as I've showed you, now, of course, it's not quite the same, but I can start with two delta pluses, do some stuff, and still have them form a bond. And that's kind of useful. Now, one thing I didn't point out that maybe, yeah, I'll point that out. Okay, so I pointed out that you do this reaction, you get the phenyl coupling. You saw the mechanism, so you know how that works. And but look, the tin is bonded to four things: one phenyl and three methyls. So why was it the phenyl that transferred? It wasn't one of the methyls that transferred, right? I mean, you don't, you know, I didn't really explain that. So the phenyl transfers, and I purposely left this as an R, so you don't know what the R is. The R is the other phenyl group. But why was it that R bonded to the palladium and not one of the methyls? The answer to that is because it's sp2, and it can better stabilize the negative charge. And so in the transition state for this process, presumably, this carbon atom, this one, bears a partial negative charge. On the other hand, if I had started out with tetramethyl tin or tetrabutyl tin, then there's no choice because I have only alkyl groups. The alkyl group will transfer. And so I start with the same right-hand piece, but instead of trimethylphenyl tin, I have tetra-N-butyl tin. Same reaction. Look at what I can do. I can actually add a butyl group. Now, this gives me a big advantage over the corresponding Friedel-Crafts. I can't make that with a Friedel-Crafts because why? Because I get cationic rearrangements and I end up with secondary alkyl groups on my aromatic ring. You don't get that here. It also gives you a very good yield. It gives you 82%. Now that surprises. Why should that be surprising? So this is much better than the Friedel-Crafts alkylation. Okay, we can see that. But why? Why am I surprised at all that this works as well as it does? Here's why. We talked about one of the elementary reactions of organometallic species, didn't we? And that was a beta hydride elimination. And the beta hydride elimination is sort of the reverse of ligand insertion. And often the beta elimination of hydrogen, hydride, can be an undesired process in a catalytic cycle, right? So anytime you have a carbon atom that's got a hydrogen, then this beta hydride elimination will take place, and you're screwed if you want something else to happen. So now you have to imagine for the tetrabutyl tin what you have in terms of an intermediate. So let's go back. The intermediate that I get for the tetrabutyl tin has R equals N-butyl. Could that undergo beta hydride elimination? You bet it can, right? But it didn't. That means that the reductive elimination here was competitive. It happened faster. If this is phenyl, of course, there's for aryl, then there's no beta hydride. You don't have to worry about it. But if it's butyl, we sure do. So the question is, how do we know when it's going to be a problem and when it's not? And it turns out that's a hard question, but you can sometimes play with the ligands. If you use different kinds of ligands here, you can slow down the beta hydride elimination. So there's a way to control that, but it's sometimes not easy. Okay, so you get this Stille reaction with an alkyl group using tetra-N-butyl tin. You end up with an N-butyl. You don't get cation rearrangements because, hey, this doesn't go through a cation. This goes through that organometallic mechanism. And you're lucky because you don't get a beta hydride elimination either. Okay, so these are some of the reactions of phenols. Turns out phenols are useful, are commonly encountered in industrial settings too, because it is the industrial preparation of not only phenol, but acetone too. So cumene, which is isopropyl benzene, is easy to come by from the petroleum industry. And this is usually catalyzed, this reaction. You can get this cumene hydroperoxide, which is a fairly stable peroxide. You can actually buy this stuff, okay? So how does that reaction take place? Well, that's a radical mechanism where the oxygen forms abstracts a benzylic hydrogen atom. It forms a benzylic radical. Now, the benzylic radical that you get, where I'm pointing to, right there, is that going to be a stable radical or not? Yeah, it's going to be very stable. Why? Because number one, it's tertiary, and it's benzoic. So yeah, it's going to be one heck of an easy radical to make. And so this process is probably going to be fairly straightforward. So making ketene hydroperoxide, easy. Then you just treat this with acid. Reversible, and I should show this as a reversible step. You can protonate the end oxygen atom, and then look what happens. You end up with a migration. The phenyl migrates to that oxygen, and at the same time, this water departs. So you get this stable cation. Why does the phenyl migrate? Well, look, this cation is like the one I showed you earlier this morning. It's resonance stabilized with the oxygen. This is going to be the important resonance structure because this is the structure that has complete octets. And then water can intercept that cation. So this is kind of a rearrangement, right? So the phenyl migrates, water leaves, and water comes back. And you get a bunch of proton transfers. Lose a proton, gain a proton. And that gives you the conjugate acid of acetone and phenol. And so this is the industrial way you make acetone and phenol. I'll repeat this process when we meet again on Friday. Now, I want to tell you something. You've all got, all of you except for these people, I can't seem to give these away, I don't know why. All of you have had your exams and you've seen the solutions. The class did not do very well, okay? So you guys figure out why. Take a look. I know it's painful, but you need to do this. You need to go over your exams, figure out what you missed, look at these solutions, and figure it out before the next one. There's another one coming up in a couple of weeks, okay? So please take care of that.